in bioprocess engineering, they will cover it to you again. Okay, cell growth, etc. They are going to cover again. But nonetheless, you can. There are very nice material available for that portion. By the way, am I audible? Should I speak softer?
No, sir, you're perfectly audible.
Perfect. So you will cover it. I will indicate, let's spend 10 minutes and then I will just summarize some of the things that I was trying to do in the third hour. I will summarize it for you today. Okay. So that all the yield coefficients. So there are too many yield coefficients in metabolism. If I start doing everything that was yesterday's class, okay, yeah, but I will do what we need for the remaining 4 hours that we have to do on the bio portion. Okay, so I will summarize the important aspects of that, but you have to still read the doubling time of cell growth, the exponential growth phase, and the integration of the basic growth equation, and how long it doubles in. Okay, I will indicate all of those right now. So if I may share. The trouble is, can you see this screen?
Not yet, sir.
No?
No, sir.
This is a whole book, right? So I don't know why. Okay, let me give you the name of the book. I don't know, it's not coming, not a problem. So the name, so yesterday's 3 hours, what we were to do, you have to read from the book. It's called Bioprocess Engineering. That's the title of the book. Please take it down, Bioprocess Engineering. And it has a subtitle dash basic concepts. Basic concepts. It's available online. The authors are Michael Schuler, Michael L. Schuler, Schuler, Michael L. Schuler, and Fikret Kargi, F. Kargi, Kargi. It's the second edition. I mean, there is an edition after that, but that's not available online. You are going to be able to find the second edition from Prentice Hall of 2001. Now, in that, you have to go through some sections in chapter 6, how cells grow, because I don't have time again to do all the growth kinetics part today. Okay, so there's a chapter 6, how cells grow. You don't have to do the whole chapter. I will indicate you the subsections to simplify. Okay, so what you need to look at is section 6.2.2. Section 6.2.2. It is growth kinetics in batch culture. So basically what it tells you is the typical batch growth curve for an organism, what it looks like. It has 4 phases. The lag phase, the exponential growth phase, which what we are interested in, a deceleration phase, and a stationary cum death phase. Okay, so that's called the batch growth cycle, and the 4 phases are very nicely described: the lag phase, the exponential growth phase, a deceleration aspect, a deceleration phase, then everything growth becomes stationary with time, and finally it dies. The organism dies, and all of those are given on page 161. Okay, so that's you have to look at that figure 6.3, typical growth curve for a bacterial system. Okay, so you must know all those 4, or sometimes people classify them as 5 phases, because stationary and death are classified separately, doesn't matter. I combined them in one. So those phases you should be able to on a curve you should be able to recognize. Okay, so it's very nicely given in figure 6.3 of the section 6.2.2. Okay, it's page 161 in the book. So ये आपको पढ़ना है. Then it gives you a description what happens in each phase. You can quickly skip through it. It's that is something you are going to again come when you do bioprocess engineering or maybe even bioprocess technology. They may tell you all of those things. What I was particularly interested to cover was the exponential growth phase. इसमें क्या है? What happens here? The growth rate is of a first order, so we can easily quantify it. And if X is the biomass and biomass concentration, then dx by dt is some mu, some constant times X. And we know the initial biomass concentration, okay, at time t equal to 0 is X is equal to X naught. So you can integrate that ln X by X naught is equal to mu into time. And so X is equal to X naught e to the power mu times time. It is over mu t. That is the standard equation, and from that you can find the constant mu, or the inverse of that constant is the tau, which is it has units of time times, and that is generally given as ln 2 upon mu, and mu is your coefficient that I wanted to describe. Okay, and later you are going to be able to give a meaning for what mu is, and that's something you are going to do in terms of growth rate, specific growth rate, etc. You're going to do. Then what it also does is it the next section, say section equation 6.11 onwards. So that is page 165 onwards. The book it defines it. There are all definitions of all the metabolic yield coefficients. Like if you want to know. You spent so much substrate in a fermentation, how much biomass was produced, or if you want to know, you have a product that is formed. We will do the mass balance aspects of this, but you have to know the definition, right? Suppose you have some substrate consumed and you want to know how many moles of product was produced per mole of substrate consumed, then that is also a yield, and they are given different symbols. So if, for instance, I am interested in the most common substrate yield, which is YXS, subscript XS, and those are defined on page 165. Okay, page 165, equation 6.11. Oh, that is something you have to understand. So the YX by S is just how much for per delta S, how much delta X is produced, okay, and with a negative sign because the two, one is consumed, other is produced, so that you get a positive value. Yield coefficients are always positive. So similarly, if a mole of substrate is consumed and some product has to be formed, how many mole of product is formed per mole of substrate consumed? That's Y subscript PS. Similarly, you can have YPX. I mean, how much product is formed per mass, per unit mass of, or mole, per mole or per unit mass of biomass which is formed, etc. Right? So this will be Y subscript PX. So there are like a dozen yield coefficients like that. I am not going to, उसका मैं ब्यौरा आप नहीं दे सकता, नहीं तो ये पूरी क्लास उसी में हो जाएगी. So that you can read on page 165. Okay. And then it gives you on page 167, it gives you all the, yield coefficients and factors for aerobic systems. And it gives tables also for aerobic growth on various microorganisms and different carbon sources, what happens. Now, all of this was supposed to be done yesterday. So this is something you have to cover, because we have to take the knowledge of yield coefficients as given, and unless we do that, we cannot start any stoichiometry or mass balance, etc. All right. So is it okay? This you will take a look at this?
Yes, sir.
Okay. What I'm, however, going to do is I'm going to summarize those yield coefficients as and when we need them. So I have to kind of change the order of things. But yeah, आप पढ़ लीजिए. The material is very, very clear. I've given you the page numbers, equation number, section number 6.2.2, and what figures you have to look at, what equations you have to look at. And of course, there are more things there, and I wasn't sure how far we will be able to go yesterday. But as it turns out, we couldn't. I mean, everybody had, I guess, the Pauli fever. So, okay. But what I shall do, however, is for our discussion today on stoichiometry of various, say, growth. So now growth, you have to, I am assuming that growth kinetics आपको पता है already, है ना? So now we have to, our job is to understand from conservation of mass, right? Do the mass balance and understand the stoichiometry of growth. Okay, or if some product is also being formed, okay, it's not essential. I mean, sometimes biomass may be your product, but not necessarily. Okay, I mean, the cell could have some other product with its own stoichiometric coefficient, and we will have to specify what those coefficients are, what those indices are in terms of atoms. Kitne atoms of C are there in a mole of product? How many atoms of H are there? How many atoms of oxygen O are there? How much nitrogen is there, etc. And similarly in biomass. And so first we have to do all of that. Once we have those stoichiometries, then we can define, we can write, you have already defined the yield coefficients. Okay, then you can write for a mole of substrate consumed. Let us say you are fermenting on ethanol, then you know what is the mole of per mass of ethanol that you are consuming, and then you have to find out kitna biomass तुम्हारा form हुआ in kg per kg or mole per mole, whatever, or mole per kg. Generally mass by mass is used. So first you have to have a stoichiometric formula for the biomass, which is something we are going to discuss. And once we have that, we will be able to write the yield coefficients that you are going to read about and which I just summarized, such as substrate yield YXS or product yield YPS. You are going to write all of those in terms of these stoichiometric coefficients of the biomass, of the cell biomass, or stoichiometric coefficients of the atoms that are there in a mole of product, etc. And that is how we will do that. So we are going to come back to the substrate yield and etc. But now written in terms of formulae. Okay, so the screen is not sharing, but did everybody get that reference?
So we'll look for it. Like,
yeah,
I haven't started looking for it yet.
Yeah, you get it. Fikret Kargi and Michael Schuler, bioprocess engineering. And this, I think in the third year you follow this book also. There are some other books. This is a simple book, so I purposely chose this. Normally, you know, we used to do IBAS book, Shuchi IBAS book, but that's a little more complicated. And since we have, no, I mean, bioprocess engineering, they may follow, or they may follow Bailey and Ollis. I mean, that's a nice book to them. It's and then there are some more, but for our purpose, I've chosen a very simple chapter 6, which is very clear. Okay, this is something you all will have to do. Okay, I mean, that is what we were to do yesterday, summarize very much in a nutshell, given in a nutshell. Now, what is it that we want to do in the next 3 to 4 hours of this bio part, and then we are left with the energy balance for the chemical reaction. So, see, now in the bio part, basically it's the overall balance that we do and the system boundaries that we draw are very analogous to what we have done for the minor. You remember we drew all the system boundaries, fresh feed, mixed feed, and then of course now the nomenclature of the process units will change. That's all. So basically what you will have is in the center a fermenter. Okay, a fermenter. Then on the left of it, let us say a mixing chamber, a mixer. Then since fermenter has all sorts, as I told you, it will have a broth with solids, and you will need a settler on the right of the fermenter. I'm assuming the flow of the feed is from left to right. And then from the, assuming that it's not the particulate matter, but the decanted system that is product, then you will have draw a product stream from the top or distillate of the settler. Very similar to what we did for the mass balance and the crystallization, etc. Okay, and now to this we can also add a recycle stream from the settler going all the way back to the mixer. Okay, so you have a mixer, then a fermenter, then a settler, then a product stream from the top of that settler, and from the bottom of the settler, let us say you are drawing a recycle stream which goes into the mixer, and into the mixer is fed fresh feed. So it's exactly analogous to what we did in the chemical mass balance. And now again, I don't have to summarize again all the boxes we can draw. The first box, let's call it box number 1, is the box which will enclose the mixer come with fermenter and settler. That's box 1, overall balance, just as we did. Then box 2 is a balance about the mixer, which will have the recycled stream and the fresh feed. Okay. Then the fermenter is your reactor. Okay, so this it would be balance around the reactor or the fermenter, which would have the combined feed coming from the mixer. Okay, and that is unit 3. I mean, or rather, rectangle, you can enclose it by, let us say, 3. And then you can have a 4th unit, the settler, and you can have a balance about that, which is the exit stream from the fermenter, and then the product stream coming out of the settler, and the recycle stream coming from the bottom, right? Exactly the same. But now there is one problem. These are the system boundaries are okay. But if you want to do mass balance, there is one difference. There is one difference from the chemical aspect. There is one problem which we didn't have to worry about for the chemical system, or even for the reacting chemical system. We knew the reaction, and unfortunately here things are just a bit more complex. So are you understanding what I am driving at? You see, what the point I'm insinuating is that in the chemical system, and we did reactions also, material balance, we haven't yet done reactive energy balance, that we will do very soon. In that reactive material balance, you already knew the reaction, like we did complete combustion of alkanes or a fuel, and you can also do incomplete combustion. You knew the reaction, and you knew what are the species, and you knew what the chemical formula of those species were, right? So you took, let us say it was CH4, you burnt it with, combusted it with oxygen, and for complete combustion you got the CO2 plus H2O, and you wrote a balanced equation, and you knew how many atoms of hydrogen are there in the methane, how many atoms of oxygen are there in CO2, and so all of those things were known. Now, when we are doing cell growth, we have to take the cells also as a product of the reaction, and we have to represent those cells in the equation of the reaction. Right? I mean, we need to know the composition of the cellular material. Because unless we know what the stoichiometries are of the cellular material, and then how it is combusted and whether it is giving only biomass as the product or it is giving biomass plus some other organic product in an aerobic cell growth system. And of course, it will give you CO2 and H2O. Those are indeed the final products. But the problem is that you need the reaction equations for growth and product synthesis. You have to formulate them. And you do not have the stoichiometry. I mean, how
Actually,
do we? Huh.
sir, sir, do you have like a slide or something? Because it is actually a bit difficult to visualize all that you're trying to tell us without the visual medium.
I don't have a slide for this. Um, I
So,
only
like
had
the ones
slide.
you prepared for
Yeah, but I
mass
don't have a
balance.
slide for this. Doesn't matter. I will maybe dictate it to you. I don't have slide for this. I only had slides for the. I mean, today actually we were going to start chemical thing, but then since yesterday thing got, I thought that I should tell you what you have to read. I only have slides for the batch growth curve, which is figure whatever figure I gave you. I mean, I forget. Page 160, whatever something 66.3 or whatever it was.
Yes, yes.
Okay, but doesn't matter. Don't worry.
Okay.
I will give you the important equation. उसको आप लिख के and anyway, the point I'm making is, let us say you represent the cell as C times some subscript W and H, capital H times small x and capital O times small y and N times small g. We have to know small w, small x, small y, small g. In other words, 1 mole of the substrates, how many gram atoms of carbon it has, how many gram atoms of hydrogen it has, how many gram atoms of oxygen and nitrogen, and you also need to know the biomass that is produced, which could have generally we take per atom of C, so C is 1. But then with respect to 1 atom of C in the 1 mole of the biomass, how many atoms of H, capital H, hydrogen, oxygen, nitrogen, etc. are present? This is not, it has to be determined by elemental analysis, by experiment, or we have to give it to you, right? So unless I know this metabolic stoichiometry, I cannot do any mass balance. In other words, I have to know the exact chemical formula for the substrate, the product, the dry biomass, and with all the coefficients like small w, small x, small y, small whatever z that which I shall dictate to you. And how are you going to do a balance unless you know what the equation is for aerobic cell growth? But the aerobic cell growth equation is not as straightforward to determine as your methane combustion or alkane combustion or some other fuel which is being combusted, and or a water gas shift reaction, for which we all know from our previous experience and our knowledge, we know all the stoichiometries and we know the exact reaction. लेकिन यहाँ पर क्या equation लिखेंगे हम? Let us assume that the extracellular products for the moment formed are only carbon dioxide and water. That simplifies things. So, I mean, we want to go to one more further level, but we can't do that today. So assuming that something is taken up and something is produced in significant quantities during the cell growth process by the cell, let us say the extracellular products that are secreted are water and carbon dioxide. Later we will add some more thing to it, and there is of course the solid, the biomass. उसका भी हमें constitution पता है होना है, हमें उसका elemental balance we have to determine. Okay, so please write down something like growth stoichiometry and elemental balance. So now what is happening is you have a substrate, and we gave it a formula C subscript W, H for hydrogen subscript X, oxygen O subscript Y, and capital N subscript Z. So this we are taking as the chemical formula of the substrate. For instance, a very good example is glucose. So small w is 6, Z is 0. There's no nitrogen. So, and X is 12 and small y is 6. So we have to write the mass, the balance equation, and we always like glucose में वहाँ nitrogen नहीं है, but we need a nitrogen source also. In every aerobic cell growth thing, we have oxygen in the aerobic thing. So you will have oxygen, and but you will also have a nitrogen source. So उसका भी हमें formula लिखना होगा. Okay. So for the moment, if I assume that only CO2 and H2O are the products, what does this overall equation of cell growth in the anaerobic system look like? That's what we want to determine. Why do we want to do this? Well, all your atoms in the substrate of carbon, hydrogen, oxygen, yeah, and then and nitrogen, and any other elements if there are. Sometimes you could have heavy metals, etc., or some other metal, etc. They are all consumed during the growth process, and they are incorporated somewhere else. So, for instance, they may be distributed into the all into the biomass, or it could be more complicated, and some part of the carbon goes into the biomass, and another thing is excreted as a product, which is different from the biomass, which may be. Right now, we are taking that biomass is the product. Later, we want to have some other product. So then you have to worry how many atoms of carbon, hydrogen, oxygen, nitrogen went into the biomass, how many went into the extracellular CO2 and H2O, and if there is a separate product other than the biomass, how many of those atoms went into those product. Now, let us say you are given a problem that in the bioprocess that you are considering, maximize some product yield. In other words, for 1 mole of substrate that is consumed, maximize how many moles of the second product other than the biomass is formed. Then we call that again, we can quantify that again by a yield coefficient, Yp subscript S, Y subscript Ps. Okay, and we can actually find from this balance equation what is the maximum theoretical yield of the product with respect to consumption of a organic substrate. Kitna maximum you can get. Then you can compare it with the experiment in the fermentation data, and you will be able to tell how close to that theoretical maximum you are reaching. And the theoretical maximum can always be found. That is what I want to show to you today. So we want to write the overall equation for growth for an aerobic cell system in which the only product is biomass. Okay, so please take it down. So you have the formula of the substrate, CW, HX, OY, NZ. Okay, so that's 1 mole of the substrate. It's combusted with A moles of oxygen, O2. So A times O2. Now, ये तो nitrogen source also is required. So this it has the formula B moles, so B times H subscript G for, so G atoms of hydrogen in the nitrogen source, O times H, OH, H as subscript, and N times I. So the left hand side of the growth equation is CW, HX, OY, and Z plus A moles of molecular oxygen, giving you B moles of nitrogen source written as H subscript G, O times H, and subscript I. Okay, that is the left hand side. Now, what about the right hand side? Well, you already know that there is no product other than biomass. So you just have to worry about the constitution of the biomass. So I told you biomass is carbon, hydrogen, oxygen, nitrogen. And we have to give different stoichiometric alphabets for each of them, say Roman, normally Roman for biomass, plus CO2 and H2O. Okay, so the right hand side then for the biomass will have C moles of the biomass, and always the biomass is expressed as per gram atom of carbon. So the constitution of the biomass is capital C for carbon with subscript of 1 always, H times alpha, H alpha, O times beta, N times delta. So C H alpha, O beta, N delta. That's the formula for the biomass. Dry biomass, I should add. You have to dry it, okay? Plus D moles of CO2 which are produced, and E moles of H2O. So this is your basic cell growth, aerobic growth formula, equation. So in this, CH alpha, O beta, and delta is the chemical formula of the dry biomass. CWHX, OY, and Z is the chemical formula of the substrate. A, B, C, D, E are the stoichiometric coefficients, which are all unknown, unlike the chemical equation. We have to determine them experimentally. How many moles of oxygen were used per mole of substrate? How many moles of nitrogen source were used per mole of substrate? How many moles of biomass was produced per mole of substrate? Etc. Same ditto for carbon dioxide and water. So A, B, C, D, E are all the stoichiometric coefficients, and all written on always on the basis of 1 mole of substrate. So how many moles of oxygen are consumed per mole of substrate? A moles.
A.
Right? How many moles of CO2 are formed per mole of substrate that reacts?
D.
D moles. Wonderful. So this is the, of course, I mean, I am not saying this is anything great. In fact, we find that since I am interested in ATP form, what we find is this is grossly inadequate. And I have to, at most, for instance, a coefficient I would be interested in is if I consume 1 mole of ATP, how many moles of biomass is formed, or how many moles of extra some other product is formed. That gives me more interesting information. But anyway, I don't. This is not my research course or anything like that. So I would be very much interested in such coefficients which give us very valuable information. But the thing is, this is what they call a structureless model. Absolutely simplest, structureless, macroscopic view. Yeah, you can say it's a very macroscopic view of metabolism. यहाँ पर my supervisor would laugh. One of my supervisors, I had more than one. I mean, he never believed in unstructured models. So he will say इसमें तो कोई structure ही नहीं है, detailed structure system का नहीं है, and you're only basically it's a very you're only considering components that is interacting directly or exchanging with the environment, like carbon dioxide, H2O. You have consumed the substrate, you are secreting, I mean, there's biomass as formed as product, etc. So it's a very simplest type of aerobic growth, cell growth equation that you can write. It doesn't include ATP, it doesn't include NADH. So I mean, I am not saying it's really great, but this is all we will do for our course. And along with, we will add product formation. So, I mean, we are excluding the multitude of important energy currency molecules and redox systems like NADH and ATP. I mean, these are integral to the metabolic process. But then, they are, you can't say that they are exchanged with the outer environment. वो बॉक्स जो आप ड्रॉ करते हैं नंबर 1, उसके बाहर या फर्मेंटर नंबर 3, उस विच आई कॉल इज यूनिट 3, उसके आउटसाइड में कोई एक्सचेंज नहीं है इनका तो इंटरनल सर्कुलेशन ही है ना NADH और ATP का. सो दैट इज व्हाई दीस मेटाबोलाइट्स आर ऑलवेज प्रूव्ड वेरी डिफिकल्ट टू क्वांटिफाई. सेल के अंदर क्या है, कॉन्सेंट्रेशन क्या है, कौन सा रिएक्शन हुआ. I mean, in vivo biochemistry is still a very difficult subject in its infancy. Okay, almost all our measurements, none of the measurements may be in vivo, right, of these metabolites. Okay, but the thing is, we are only interested in the balance of metabolites or constituents that have a net exchange with the outer environment. So ATP is not there, NADH is not there, vitamins are not there, any mineral elements are not there. These are also अपटेक होता है इनका मेटाबॉलिज्म में, लेकिन इनको हम इंक्लूड नहीं कर रहे हैं. ओके, हम अपनी स्टोकियोमेट्रिक इक्वेशन में वी आर एक्सक्लूडिंग दीज एजेंट्स. सो प्लीज अंडरस्टैंड दीज असम्पशंस. ओके, so it's a very simplest equation of a macroscopic equation for aerobic cell growth that we can write. But the interesting thing is, even this very simple thing gives us some information, and it can be used for a thermodynamic analysis. It's not that it is completely irrelevant. So what you are saying is, we are taking conversion of substrate, oxygen and nitrogen, and we have put that into a cell growth process where biomass is produced. In other words, suppose a cell is a black box. That's what we are saying. कोई internal structure नहीं है. My supervisor will be shaking in his grave, but anyway. So we are saying substrate goes into the cell, into the black box, CW, HX, OY, and Z. A moles of oxygen enter from outside. A nitrogen souls B moles with H subscript G, OH, Ni enters the cell. And what exists is the cell biomass, which is C moles of CH, alpha, O, beta, and delta, and D moles of CO2 and E moles of H2O. Okay. Now, there is no objection to representing a molecular formula for cells. Like we have idealized this biomass of the cell as CH, alpha, O, beta, and delta. This is its biomass, यही composition है उसका. Now, I don't know if Kargi has it, but at least in research papers, the composition, elemental composition, at least for E. coli systems, for Escherichia coli system, has all been done. What is if carbon is the element, so how much of the percentage of dry weight is carbon, oxygen, how much of the percentage constitution is. I mean, any microbiology book will also should give this. Similarly, NH, phosphorus, that's a very important component which we will not be considering. And of course, all the alkali metals and alkaline earth elements, very important. Magnesium, calcium, so important. And also anions like chloride, which is the principal anion many times, and iron, etc. All of these have been done for at least bacterial systems. Like Escherichia coli पर इसमें wide range of elements है, लेकिन 95% of the biomass is accounted for by these four major elements: C, H, O, and N. And that is all that we are considering in our very simple mass balance. All right. Now we can complicate it, and different systems have a different nitrogen content on the average. I mean, bacteria have about 10% nitrogen content. Fungi have a very different lower content, etc. So it totally depends on culture conditions actually, and कौन सा substrate आप use कर रहे हैं. So ऐसे there are differences, but thing is, composition analysis has shown that basically the biomass can be represented by CH 1.8, O1, O 0.5, and 0.2. This is an averaged biomass composition over so many systems. So that is like it will be there in every textbook. Of course, you will do an elemental analysis of the biomass. I mean, Sri Krishnan's and Zia, they do this quite routinely. They have an CHN elemental analyzer. It's been used by every student. So CH 1.8, O 0.5, and 0.2. This is the general formula. Suppose the composition analysis of the biomass are not available, then this is the general formula of the biomass. Okay, but we are to actually find all of this average molecular weight. If you take the general formula, then the average biomass CH 1.8, if you do that, the average molecular weight will come to be 25. Okay, but इसमें भी क्या है? There are problems. Actually, ash is always there in every biological system. It can be as low as 5%. It can be as high as 35%. I mean 40%. That is not even accounted for here, right? Nowhere have we accounted for residual ash. So उसको भी हमें generally balance करना पड़ता है, because that will also have CH, and so for the moment I have ignoring all those complications. Okay, but generally this is found by experimental analysis. But what we are going to do is we are going to see how do we determine all the unknowns in this simplified macroscopic cell growth, aerobic cell growth equation. We will have to identify what are the knowns and what are the coefficients that we have to evaluate. Okay, and then next time on Wednesday, we want to write those equations. Okay, so what have we done today? I summarized to you what you need to do based on the 3-hour class that I was to hold yesterday. I have given you, the book is available online. If there's a problem, let me know on my Wednesday. You are supposed to do section 6.2, and I indicated exactly which figure and batch growth में क्या तुम्हें पढ़ना है, and what yield coefficient definition you have to see, because I don't have time to keep on giving the symbol for every yield coefficient. There are at least dozen yield coefficients. Okay, I only named you two of them or three of them today. Like the substrate yield, the very common thing which we will use a lot, because 1 mole of substrate is consumed, how many moles of biomass are formed, or if 1 kg of substrate is consumed, how much kg of biomass is formed. That is Y X subscript X, most common yield coefficient. But there are so many, and as I told you, my interest is, for instance, the yield based on ATP, and वो तो हम पहुंचेंगे नहीं, but that makes subject very interesting. But so like that there are dozens of yield coefficients. I don't have time to define all of them, but you can please look at them in Kargi and Schuler's book. Okay, इतना आपको करना है. Then what I tried to do is I said, okay, we are going to start from the simplest macroscopic balance. And I told you what is the difference between this and the chemical system कि यहाँ पर हमें वो formula नहीं पता substrate, nitrogen source और biomass का. Okay, and I'm assuming कि there's no other second product form. That biomass is the product. So that's another assumption. I am assuming that there are no heavy metal and other elements. And ash का में कोई जिसमें ash will also lose a lot of contain or a lot of the C, H, and etc. So that I am taking as 0 in this overall equation, and I gave you that overall equation. And usme all the thing was that we need to find out, we need to know small w, small x, small y, small z, alpha, beta, delta, etc. and all the stoichiometric coefficients. So we need to find out कि इस equation में कौन-कौन से unknowns है और हम कितने balancing equations लिख सकते हैं. How many balancing equations can we write? Okay, so this is our assignment for next class. So I think you have I think we should continue the bio thing until this is done, because that's what I was going to do on yesterday. And let us see, we need, I estimated we need about total of 6 to 7 hours for it, 7 classes for it. So we have done only 4, we need another 3. So maybe this week, let's finish that. But next Sunday, we nonetheless have to we have to have the extra class next Sunday, because we need another 6 classes to finish the energy balance on reactive chemical systems. Okay, so you need to cooperate, वो bunk नहीं कर सकते. All right. Is that all right? Thank you.
Yes, sir.
You have all the material. If the material is not there, I will find a way to share it with you. Okay. Thank you very much.
Yes,
happy Diwali to you all.
Thank you,
Good
sir.
to have you, Devapriya, also. I mean, I missed you yesterday. Ashi, you too.
Sir, there was a major electrical fire in my house, so I
Oh God.
gained access to electricity.
In fact, you'll
only
be
after.
surprised. You'll be surprised. There was an electricity problem in all of our, not only our block, our entire complex. But however, after some frantic calling, it got settled. And there's a number, I mean, anyway, it was settled by 10:30. But anyway, as it turned out, it was not required. Okay, all right. Good luck. Please do all of this, and we will continue on the lines I indicated. Okay. And I hope that all the fire is under control. Okay, thank you very much. Ashi, all especially. Okay, happy Diwali to you all.